Hello, my name is Hiti. I'm going to talk about Proxyless neural architecture search, which has direct neural architecture search on target task and hardware. So I'm going to give you a code review for how Proxyless NAS is being architectured. There are two basic approaches for NAS: proxy-based approach and proxy-less approach. In proxy-based approach, as there are many different neural network architectures and optimization techniques to consider when we design a low power consumption application. So when there is a proxy-based approach, it is often difficult to find the best neural architecture for a particular task, as there are many different architecture possibilities. So the proxy task is being transferred to the target task and the hardware. So there are three layers in considering the proxy-based approaches, where learner is the first layer task, and then it is being constructing the architecture and goes to the proxy task, which is transformed to the target task. So a, this takes more time, computational time, and more memory hardware. So instead of avoiding such limitations, we have a proxy-less approach where we directly construct an architecture on the target task and the hardware without considering a proxy task. In proxyless approach, this is one of the first neural architecture search algorithm which directly learns the architectures in large scale data set without any proxy. Uh, while in proxy based approach, it considers small data sets and builds the architecture for small data set and then transfers it to the target task. So in order to avoid this um, overhead of building architecture on small and then transferring it to the larger or the target task, this is taking more computational time, as well as it is a burden to have three layers in the construction of the architecture. So we have proxyless architecture where it builds and learns the architecture on large data sets directly. So this removes the repeated blocks which comes during the architectural design. As neural architecture search algorithm automatically finds a deep neural network architecture, it meets the performance and accuracy requirements on the target task. The advantage of NAS is that the state-of-art solution should be built for low energy consumption. So, to have a neural network architecture with different combination of layers, which automatically is designed to find a architecture which achieves the desired performance, we need to construct a over-parameterized network considering the proxyless NAS. So when considering the over-parameterized network, we first have to uh, use a technique which automates the neural network architecture for various tasks. So in order to do this, we denote a neural network as N, where each edge is represented as an edge in the cyclic graph. This acyclic graph is a directed acyclic graph. So when you have some operations performed on each edge, this is a mixed operation that has n parallel paths, denoted as n0. M M of O, where O is the primitive operation for that particular candidate. So there are n candidates, there are going to be n primitive operations. So the overparameterized network is expressed as n consisting of edges as MO of 1 to MO of n, where MO of 1 is the mixed primitive operation for a particular candidate 1 up to candidates n. So in a layer there are going to be 1 to n candidates, and so the operations are going to be n operations. When we have given an input as x, the output of the mixed operation MO is defined based on the output of its n paths. So there are n parallel paths. Therefore, we will be having n parallel operations. So we're going to consider the sum of all these operations, and this is denoted as MO of X in one shot. But in considering darts, these are the two branches for over-parameterized networks, that is one shot and darts. In darts, you find the weighted sum of O of I. So in order to calculate the weighted sum, we calculate the weight based on the real value architecture parameter, that is sigma of I, which is expressed as MO of darts of X, is equal to 1 to n, where the real value architecture parameters are being considered along with the primitive operations. So you get the equation as summation of I equal to 1 to n for Pi into O of I of X. So, but in one shot you only have O of I, because you get only the sum of all the primitive operations. The output feature here for all the n paths is calculated and stored in the memory. So as all of these n paths are stored in memory, the memory limitation is going to exceed, and thus the hardware is going to require more space. So in this case, we have a memory issue which occurs. This is being solved by the idea of path binarization, wherein when you train a compact model, it involves only one path because there are no parallel paths considered. For constructing the over-parameterized networks, we consider n parallel paths for calculating its weight parameters. We need to binarize the path to have to overcome the issue of memory. So when you have n real value architecture path parameters, you have to transform them into binary gates. So you use the function g, which is equal to binarize pi to pn. Binarize is either 0 or 1 based on its probability. So for a particular architecture parameter, we transform that path weight into binary gates for all the n parallel paths. So we have 1 to n parallel paths. We consider 1, 0 up to the number of edges or the paths in the particular network, considering its probability and finding out the binary gates. Based on the binary gates of G, the output of the mixed operation is given as G summation of I equal to 1 to n Gi of Oi, where O of 1 of X with probability P1 is for one edge or one path, and for n number of paths, it is going to go up to O of n of X with probability of Pn. So this is the equation which we find for learning a binarized path based on the transforming a particular architecture parameter into binarized weighted parameter. So by using the binary gates, we only have one path of activation which is active in the memory at runtime. So as there is only one path of activation which is active in the memory, the use of computational or the CPU hours is going to be less. So the order of magnitude in memory is saving. That is the more than the order of magnitude which was previously used. So the memory saving is more, and so low power consumption is achieved. This is the architecture which shows how we train the binarized parameters, and here if you see, there are two ways of learning both weight parameters and binarized architecture parameters. When you have to train the weight parameters, first we freeze the architecture parameters and then we sample the binary gates according to the equation of G is equal to the binarized P1 to Pn, where we have applied probabilities for every path. So this is based for each batch of the input data. Then the weight parameters of this active path are updated. The updation is done using a standard gradient descent on the training set. When you consider the weight parameters, you update the weight parameters based on the binarized gate function. So in this case, in this time, you first freeze all the architecture parameters when you have to update the weight parameters. But the second option is learning with binarized architecture parameters. When you have to learn with binarized architecture parameters, we first have to the goal is to update the architecture parameters. So the weight parameters are frozen in this case, and uh, when the weight parameters are frozen, we reset the binary gates and update the architecture parameters on the validation set. These two update steps are usually performed in an alternative manner. So once the training of the architecture parameter is done and completed, we can derive the compact architecture by pruning the redundant paths. So you would prune the binary gate output, which is 0, and you keep the binary gate output, which is 1. So we derive a compact architecture in this way by following the pruning based on the binary gate output, and thus we just choose a path in this uh, training architecture with the highest path weight. So the path weight which is highest is being considered and chosen for the further uh, layers, and it is forwarded to the further layers. So now the concept of neural architecture search is being clear, where we know we use the Proxyless approach in order to automatically design a neural network architecture. How the code is being structured in for this neural network is being explained in the further slides. So the code review consists of three different major modules. First is the search, training, and Proxyless NAS. In search, you have got search code for neural architecture, the code for how to search and how to find a neural architecture based on NAS, which is a proxyless approach. Training, it has training data set for code for training the searched modules. And Proxyless NAN has pre-trained modules for TensorFlow as well as for PyTorch. When you consider the code structure for Proxyless NAS, you have got three approach modules which we just read on, that is search, training, and Proxyless NAS. This Proxyless NAS is for PyTorch. We are considering PyTorch as the platform or the pre-trained module here. The search consists of modules, data providers, and utils. We'll first go on what search utils consist. Search utils has got three main classes, that is latency estimator, my modules, and PyUtils. These are the three programs which are executed in utils module. Um, in latency, the first one is the latency estimator. In latency estimator, you have got different methods which implements and defined as download URL, class latency estimator, init, repository shape, predict. Predict has got different layers in it. Basically, for NAS, This technique is an automated technique. So it designs the architecture for various tasks based on the recurrent neural network, and it uses the reinforced learning to compose the candidate deep neural network architecture. Once you get a deep neural network architecture composed, that is the compact model, by finding out the highest path weight, you get a compact value module. This is being trained and tested using the validation set. So when the validation accuracy is being used as a reward function, you then optimize the controller's next candidate architecture. And in this way, you keep on doing this technique. So you automatically design a neural network architecture based on the recurrent neural network controller and training and testing using validation set. Uh, so when you have to find the latency estimator has got a function where it finds the layer type. So there are four major layer types: convolutional, convolutional 1, logit, expanded convolutional. Convolutional is the initial 3 by 3 convolutional with stride 2. In the figure for training the binarized architecture, we just saw how sample input data is being connected and forwarded to the next layer, which is the weight parameters. So how do you update the weight parameters? It is based on the convolutional layer. So if the convolutional layer initially is 3 by 3 convolutional layer, then the layer type here in the code is defined as convolutional, wherein the convolutional one is 1 by 1 convolutional upsample, which has been increased by 4 times. It increases the number filter by 4 times. The logits, here logits layer type, it has all the operations which are being performed after the convolutional one. And expanded convolutional, which is the mobile inverter residual, so it is compatible on the mobile NAS. The input, this feature has input shape which consists of H, W, and the number of channels. Number of channels can be inward channels as well as outward channels. For the particular path from one node path to the other node path, so there are n parallel paths in this case. So based on the particular layer, you're going to have the input shape derived, and the output shape is going to have again the height of the layer, the weight between the paths of the nodes in the network, and the number of channels in the network. Expand is the expansion ratio, which defines how your network is feasible to expand once the neural network has been constructed. The kernel size is how much kernel size is utilized in order to perform the computational operations in the particular layer of the network. So this is what is going on in the latency estimator, where it majorly depends on the layer type, the input, output, expand, and kernel. These are the functions or the methods used in latency estimator. The next the next feature which we are going to see in this code structure is the search, and inside search it is utils, and utils it is my modules. So we saw latency estimator. Now the next part is my modules. In my modules, it has basically got two major classes. One is my modules and my network. So my modules is basically going to give you the module for your network. And to build a network, you have to pass my modules to the my network class, which is a parameter or argument to the my network class. So you pass So you consider my network as a constructor with my module as the class, which is the base class, and my network is the parent class, or for the my module class. And in my modules, the methods which includes our forward, which has got the forwarding path, how the network is being connected, and what are the paths or edges which are having forward uh, weights to the next candidate neural network architecture. And in module str, this is one function where you have the stride, or the module stride, being defined for the particular layer. Config is how you configure your modules in the particular network. Based on that, you have build from config. So you build a module based on what is defined in config. Get flops. So these are the number of flops you have in your module. So these flops are either, if it is based on the concept of pruning and keeping when finding the binarized gate function. So in this case, you have flops which are either with the which are either within the module or within a particular path of your structure. And in my networks, you have different methods, that is forward, build from config, get flops, set bn parameters, get bn parameters, init module, get parameters, and wait parameters. When you see set bn param, this is nothing but set batch normalization parameters. And when the batch normalized parameters are set, you have to get those parameters. And so there are two different methods for batch normalization, get and set. Init model is based on three conditions of, like, if the neural network is a convolutional layer type, or it is a batch normalized 2D layer, or it's a batch normalized 1D layer. Based on these three conditions, it will build its network and for the particular module. Get parameters, it will get the parameters based on the real value weighted paths. So it will transform the real value weighted paths into binarized paths and get those parameters. Weight parameters are the mixed operations, that are the sum of the weight of n primitive operations. In PyTorch utils, which is the next part in utils, uh, in the utils structure, where it has got functions like, the most important is the build activation. So it is going to build it is going to have the activation function and build the activation on its activation function type, such as ReLU, ReLU6, TANH, and sigmoid. Uh, ReLU is nothing but rectified linear unit. This function is basically a linear function for values which are greater than 0, which means that it has got a lot of properties of linear activation function. When you have to train a neural network using backpropagation, you usually use rectified linear unit. So yet this is a non-linear function, as negative values are always output as 0. This function is going to be considered as linear when the values are greater than 0. So when the value has a function of rectified s equal to max of 0 to x, which means that if this function has got values greater than 0, means there are a lot of properties of linear activation function. But when the values are always negative, or which are always output as 0, at that time it is a non-linear function. So rectified linear unit has two functions in it. linear function and non-linear functions. This is based on the values which we get, if it is greater than 0 or less than 0. Rectified linear unit 6. Linear unit 6 is just an advanced uh, linear function of rectified linear unit. TANH performs the normal mathematical functionality of trigonometry, finding the TANH for a particular function or values in that function. Sigmoid is to find the sigmoid. Uh, it has a function for finding a sigmoid for the values which are always going to be an output to the to build an activation function. The other method is cross entropy with label smoothing, counting the parameters, count the convolutionary flops, detach the variables, and accuracy. Accuracy is basically how accurate, that is the state of art of accuracy for having a uh, low energy consumption neural network. The next part is the code structure for search and utils. The first now which we saw was utils, and now the next structure is for search modules. Search modules, it has basically got two major operations in it, which are mixed operation and layers. As we know that we perform mixed operations for every edge in a cyclic graph. These mixed operations has been defined in the class modules, where the file name is mix operation. The mix operation has got two major classes: mixed edge and architecture gradient function. Architecture gradient function is basically used to find the uh, gradient uh, gradient value for the sample data. In mixed edge, the methods which are included in mixed edge are set the chosen operation active, init, entropy, backward function, binarize, set the architecture parameters gradient, rescale the updated architecture parameters. So these are the functions which are going to perform the operations for mixed operation module. In mixed operation module, the class the class of architecture gradient function has got two major functions, that is the backward and forward. These are the two methods which has got backward as the backward edges and forward as the forward edges. So these are going to have inward and outward channels in its layers. So the next class, which is layers in modules, has got different types of layers. Those are convolutional layers, depth convolutional layers, pooling layer, identity layer, linear layer, MB invented convolutional layer, and zero layer. When considering the set layer from config method, in that method you see that the convolutional layer is being constructed, and the layer name is given as uh, stores the value for layer.config.pop. So whatever is there in the config, that is being popped, and that particular layer name is stored in the variable layer underscore name. This is what is happening in search modules and layers part. So when you store the layer name in the layer, it returns the build from config. Um, for class my2d layer, it has got arguments as in channel, out channel, use bn, which is usually true. Activation function is relu. Dropout rate is zero. Operations order is wait with batch normalization activation function. So the five different major operations are activation function, dropout rate, weight of the operation, and adding the modules. You add modules based on their weights and their keys. Um, the last module, which is Proxyless NAS, that is the training code, which consists of network 224 by network 224. In this network 224 into network 224, it has got init, mobilenet v2, and restnet. These are the three classes which we used for training the sample data, which is captured after building the neural network architecture using Proxyless NAS. And the Proxyless NAS in utils consists of bags of tricks and gradient compression. So bags of tricks is what trick it has to use to make the neural network more accurate, and the performance of the on various tasks has to be increased. So this is what is explained and implemented in bags of tricks. Where in gradient compression, you find the gradient based approach for handling the operations, like latency to find an inefficient architecture with less computation time, in suppose approximately 300 GPU per hour. So it uses the path level pruning to reduce the number of candidates in number of candidate architecture. So in this way, we have Proxyless NAS for neural architecture search. So to reduce the computation cost of neural architecture search, researchers have found a proposal to search for the candidate architectures based on the proxy tasks and rewards, such as working with a small data set like Cipher 10. So instead of such unit which uses proxy task, we are here using proxyless task. So the DNN network is being optimized on proxy tasks and are not um, being guaranteed to be optimal on the target task. So here we use especially the proxyless task, where the hardware metrics like the latency with our latency with approximation of number of operations or number of parameters is being optimized, and so we overcome the limitation here in case of proxyless NAS, and we propose the path level pruning to reduce the number of candidate architectures and build a gradient based approach for handling the objectives like latency, and this makes the architecture more efficient with the use of proxy based NAS. Thank you.